We are born into a world brimming with mysteries, unanswered questions that have lingered in the corners of human consciousness for millennia. From ancient philosophers to modern scientists, humanity has constantly sought to understand the vast, uncharted realms of existence that stretch beyond our planet. But there is something uniquely tantalizing about the unknowns of the cosmos. They invite us not only to question the very fabric of reality but also to challenge the limits of our imagination and perception. These questions, no matter how elusive, pull us toward the unknown with an irresistible gravity, as if the universe itself is whispering, "Come closer. There is more than you can imagine." From the earliest days of civilization, humankind has gazed at the stars, pondering the mysteries of the universe. Ancient astronomers, with only rudimentary tools, mapped the heavens and observed the regular movements of the celestial bodies. The night sky, with its ever-changing constellations and distant stars, became a canvas for our myths, stories, and beliefs. But even as we constructed narratives to make sense of the cosmos, there remained a profound sense of wonder, a recognition that, despite our most astute observations, we still knew so little. And as time progressed, we began to pierce the veil, advancing in our ability to observe, measure, and understand the universe around us. Yet, the more we learned, the more questions emerged, questions that pushed us toward the very limits of knowledge itself. In the 21st century, we are standing on the precipice of an entirely new era of discovery. A new chapter in our understanding of the universe is being written, not with the ink of historical legends or philosophical musings, but with the data collected by humanity's most powerful instruments. Among them, one stands at the forefront of this cosmic revolution: the James Webb Space Telescope, or JWST. Launched with the ambition to peer deeper into the cosmos than ever before, the JWST has begun to unravel the secrets of the universe in ways we never thought possible. It looks back in time, capturing images of distant galaxies formed billions of years ago, and it explores the most enigmatic phenomena of space, revealing a universe far more complex and mind-bending than we had ever anticipated. The JWST's mission is not just to capture stunning images, but to answer questions that have plagued humanity for centuries. How did the universe begin? What lies at the edges of space and time? Is there life beyond Earth? The answers may not come easily, but with each discovery, we find ourselves drawn further into a cosmic mystery that no one can fully explain, yet. The deeper we look, the more profound the questions become. And with each new revelation, the divide between the known and the unknown seems to grow wider. But therein lies the paradox of cosmic exploration. The more we learn, the more we realize how much there still is to discover. The universe, vast and enigmatic, constantly reveals just enough to provoke further curiosity. We may come to understand more about the origins of stars, the nature of black holes, or the formation of galaxies, but each answer often opens up new, more complex questions. It's as though the universe is a puzzle with no end, a riddle that constantly shifts, reshapes, and deepens as we approach it. And yet, this is what drives us forward: the belief that the answers, no matter how elusive, are worth seeking. It's not just scientists who are captivated by these mysteries. Every individual who looks up at the night sky feels that same pull. Whether we are gazing at the moon, observing the constellations, or pondering the distant stars, there is a profound sense of wonder that accompanies our gaze. It stirs something deep within us, an ancient, almost primal curiosity that seeks to understand our place in the cosmos. But with that curiosity comes a sense of awe, even fear. For the unknown is not only a source of fascination but also of trepidation. As we look deeper into the universe, we are faced with the realization that much of it may be beyond our comprehension, our reach, or even our ability to survive. This tension between fascination and fear is a theme that runs through the entire journey of cosmic exploration. It's a tension that has shaped not only our scientific endeavors but also our philosophies, religions, and stories. The unknown holds the promise of enlightenment, but it also holds the potential for disaster, or worse, existential insignificance. We may find life beyond Earth, or we may discover phenomena so alien that they defy all our existing frameworks of thought. What if the universe is not only beyond our comprehension but hostile to our existence? What if we are not meant to understand it at all? These are the questions that stir in the hearts of those who study the cosmos and those who merely wonder about it. And these questions are at the very core of the discoveries being made by the JWST. What it has uncovered so far has been nothing short of astounding, but the implications of these discoveries are still being unraveled. What is clear, however, is that the universe is far stranger, more complex, and more mysterious than we ever imagined. And yet, we are compelled to push forward into that mystery, driven by the eternal human desire to know, to explore, and to understand. As we embark on this journey, we must confront not only the scientific implications of the JWST's findings but also the philosophical and emotional toll of discovering the unknown. For each new discovery brings with it a wave of questions, many of which may never be answered. It's a paradox that has always accompanied our search for knowledge. The more we know, the more we realize how much we don't know. The universe, in all its grandeur and complexity, stands as both a beacon of possibility and a wall of uncertainty. And so, we continue to gaze into the abyss, not knowing what we might find, but driven by the belief that the pursuit of knowledge is worth the risk. The unknown calls to us, and like explorers setting sail for uncharted lands, we can't resist the urge to see what lies beyond the horizon. But as we embark on this journey, we must ask ourselves, what if the answers we seek are not just beyond the stars but within ourselves? What if the greatest mystery of all is not out there, but in the very nature of our quest to understand? The cosmos is a vast, ever-evolving spectacle, an intricate dance of matter and energy unfolding across incomprehensible distances. It's a world that operates by rules so far beyond our daily experiences that they often seem to defy logic itself. For centuries, humanity has peered into the night sky, attempting to make sense of the patterns, the movement of the stars, and the unseen forces shaping the universe. Early astronomers mapped the skies, following the predictable paths of the planets and tracking the movement of the moon. Yet, no matter how much we observed, the scale of what we saw was far too enormous for the human mind to fully grasp. What we learned was only a sliver of the total picture, an endless ocean of cosmic phenomena, stretching far beyond the limits of our vision, understanding, and imagination. In recent years, our understanding has begun to change. With each new technological advancement, we gain a clearer, sharper, and more detailed view of the universe. Yet, with every new discovery, more questions arise. It's as if the cosmos itself is a moving target, constantly shifting and evolving, presenting new layers of mystery with each passing day. The universe is not static, it is in a constant state of flux. Stars are born, live, and die in a ceaseless cycle. Galaxies collide, merge, and break apart in a breathtaking display of cosmic forces. New phenomena are discovered almost daily, and each one forces us to reconsider what we thought we knew. What we once believed to be fixed, immutable truths are now revealed to be fluid, complex, and far more dynamic than we could have ever imagined. The idea of a dynamic, ever-changing universe is not a new one. In fact, it was once the subject of great philosophical debate. Ancient thinkers such as Heraclitus famously posited that everything flows, suggesting that change is the fundamental nature of reality. In the cosmos, this idea rings true. We now know that the universe is not just expanding outward in space, but it is also evolving over time. The birth of stars, the death of black holes, the formation of galaxies, and the creation of new elements, all of these processes are the result of a continuous cycle of change that has been unfolding for billions of years. The most groundbreaking discovery that highlights this cosmic flux is the concept of the expanding universe. The realization that the universe itself is growing, its galaxies racing away from one another, was one of the most profound revelations of the 20th century. It was first proposed by Edwin Hubble in the 1920s, based on his observations of the redshift in distant galaxies. This was the first hard evidence that the universe was not a static entity but one that was actively expanding. As time went on, this theory was further supported by the discovery of cosmic microwave background radiation, the faint afterglow of the Big Bang itself. Yet, the more we learn about the universe's expansion, the more we realize how much we still don't know. One of the most puzzling aspects of the universe's expansion is the role of dark energy, an invisible force that appears to be accelerating the rate at which the universe is growing. In fact, it was the discovery of dark energy in the late 1990s that completely upended our understanding of cosmic evolution. Scientists had long believed that gravity would slow down the expansion of the universe, eventually bringing it to a halt. Instead, what they found was that the universe was not only continuing to expand, but the rate of expansion was actually increasing. Dark energy, which remains largely mysterious, is thought to be the driving force behind this accelerated expansion. The discovery of dark energy has raised more questions than answers. What exactly is dark energy? Why is it causing the universe to expand faster than ever before? Could it lead to a future where the universe continues to expand indefinitely, eventually growing so distant and sparse that stars and galaxies are separated by vast, unbridgeable distances? These questions, which once seemed far too speculative to entertain, are now at the forefront of cosmological research. They suggest that we are living in a universe that is far more dynamic and unpredictable than we ever imagined. But the universe's expansion is not the only indication that it is in a constant state of flux. As our telescopes and instruments have become more advanced, we've begun to detect other phenomena that challenge our understanding of space and time. For example, the discovery of gravitational waves, ripples in spacetime caused by massive cosmic events, like the collision of black holes, has opened up an entirely new way of observing the universe. These waves, predicted by Einstein's theory of general relativity a century ago, were only detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Their detection not only confirmed a key aspect of Einstein's theory but also revealed that the universe is full of previously undetectable forces and events, creating a sense of wonder and anticipation about what else might be out there. Perhaps the most astonishing discovery of all is the revelation that the universe, despite its vastness, may be far more interconnected than we had ever imagined. For years, scientists have speculated that galaxies are not isolated, but instead are part of a larger cosmic web, a structure that links galaxies, clusters, and superclusters in a vast interconnected network. The discovery of this cosmic web has reshaped our understanding of the universe's architecture, suggesting that there are forces at play that we still don't fully understand. Galaxies that we once thought were distant and separate from each other are actually bound together by invisible forces, forming a grand, intricate tapestry of cosmic connections. And yet, even as we begin to uncover the structure and behavior of the universe, we are faced with even greater mysteries. One of the most perplexing questions is the nature of dark matter, the invisible substance that makes up approximately 85% of the mass of the universe, yet has never been directly observed. Scientists know it exists because of its gravitational effects on visible matter, but its exact composition and behavior remain a mystery. Could dark matter be the key to understanding the larger forces shaping the cosmos? Or does its elusive nature suggest that we have completely misunderstood the fundamental laws of physics? At the same time, the more we explore the universe, the more we realize how little we know about the most basic elements of existence. For instance, despite the fact that we have been observing the cosmos for centuries, we still cannot fully explain the mechanics of certain celestial bodies. Take black holes, for example. These enigmatic objects, which are the remnants of massive stars, possess gravitational fields so powerful that not even light can escape them. While we know a great deal about black holes, there is still so much that remains a mystery. How do they form? What happens to the matter and energy that fall into them? And what is the true nature of the singularity, the point of infinite density, at the center of every black hole? The more we learn about the universe, the more we realize how much there is left to discover. Each new discovery opens up a world of further questions, deepening the mystery and expanding the scope of our curiosity. And this is where the true beauty of science lies. The pursuit of knowledge is never a linear path. It is a journey that constantly evolves, shifting and adapting to new revelations and insights. As we continue to explore the cosmos, we are reminded that we are only at the beginning of our understanding. The universe is in a constant state of flux, and with each new discovery, we are invited to explore the infinite possibilities that lie ahead. The more we look, the more we realize that the universe is a place of immense wonder and awe, one that challenges the very core of our understanding. And perhaps, in the end, it is the mystery itself that makes the journey worthwhile. The pursuit of knowledge, the thirst for discovery, and the need to answer the deepest questions of existence. These are the forces that drive us, that push us beyond the limits of what we know, and that propel us toward a future where the unknown is not something to fear, but something to embrace. The James Webb Space Telescope, JWST, is not just another tool in the growing arsenal of humanity's scientific exploration. It represents a monumental leap forward in our understanding of the universe. Unlike its predecessors, which were limited by the constraints of their time and technology, JWST is designed to push the boundaries of what is possible. With its unparalleled ability to observe distant galaxies, stars, and planets in unprecedented detail, it is a window into the cosmos like no other. Yet, despite its technical sophistication, the JWST also carries with it an aura of mystery, as it holds the potential to uncover truths so profound that they could challenge everything we thought we knew about the universe. Launched in December 2021, the JWST is a collaboration between NASA, the European Space Agency (ESA), and the Canadian Space Agency (CSA). Its mission is simple, yet its potential impact is immeasurable: to peer deeper into the cosmos than any telescope before it. Unlike the Hubble Space Telescope, which primarily observes the universe in visible and ultraviolet light, JWST is designed to observe the universe in the infrared spectrum. This ability allows it to see through cosmic dust clouds, peer into the hearts of forming stars and galaxies, and even look back in time to see the first galaxies that formed after the Big Bang. It is, in many ways, our greatest opportunity to understand the infancy of the universe and its evolution over billions of years. The JWST is an engineering marvel. With a mirror that spans 6.5 meters across, over 2.5 times the size of Hubble's, it is the largest telescope ever launched into space. The mirror is composed of 18 hexagonal segments that work together to collect light from the farthest reaches of the universe. Each segment is coated with a thin layer of gold to optimize the telescope's sensitivity to infrared light. This intricate, precise construction allows JWST to detect faint signals from galaxies and stars that are billions of light-years away, revealing details that would otherwise be hidden from our sight. But what truly sets the JWST apart is not just its size or its ability to peer deeper into space, but the way it has been designed to unfold in space itself. Unlike other telescopes that are built and tested on Earth, the JWST's deployment in space has been one of the most complex and daring operations ever undertaken. Once launched, the telescope had to travel nearly 1.5 million kilometers from Earth to reach its orbit at the second Lagrange point, known as L2. The journey itself took a month, and once it arrived, the telescope had to unfurl itself, like an intricate piece of origami, into its full, operational state. This process involved deploying a massive sunshield the size of a tennis court to protect the sensitive instruments from the heat of the sun, as well as aligning the 18 mirror segments with precision so that they could work in unison. The entire operation was so complicated that scientists held their breath as they waited for each step to be completed successfully. The success of the deployment was not just a technical achievement, but a testament to the boldness of human ingenuity and our commitment to exploring the cosmos. The launch and deployment of the JWST were moments of sheer awe and wonder for the scientific community, but they also marked the beginning of an even greater journey, the quest for answers. The telescope was designed with one goal in mind: to answer the deepest questions about the universe. What was the universe like in its earliest moments? How did galaxies form and evolve over time? What is the nature of dark matter and dark energy? Could there be other forms of life beyond Earth? The JWST's observations have already begun to revolutionize our understanding of these questions, offering glimpses into the cosmos that were once thought to be beyond our reach. One of the most remarkable features of the JWST is its ability to look back in time. When we observe distant galaxies, we are not simply seeing them as they are today, but as they were when their light first began its journey to us, often billions of years ago. In essence, the further we look into space, the further back in time we are able to peer. This gives us a snapshot of the universe's past, allowing scientists to study how galaxies, stars, and planetary systems formed in the early universe. By observing galaxies that are so distant, JWST provides a view of the cosmos as it was just a few 100 million years after the Big Bang, when the first stars and galaxies were taking shape. These early moments in the universe's history are some of the most mysterious and least understood, and JWST's ability to capture these distant, ancient light signals opens the door to understanding the very origins of the universe itself. Perhaps even more thrilling is the JWST's potential to reveal new, unknown phenomena. With its ability to detect infrared light, it can peer through cosmic dust clouds that have previously obscured our view of star-forming regions and the centers of galaxies. In many ways, the JWST has the potential to uncover new and hidden aspects of the universe that we had no idea existed. For instance, it may allow us to directly observe the formation of stars and planetary systems, something that has been nearly impossible with earlier telescopes. The detailed observations of young stars and planets in the process of formation could provide crucial insights into how our own solar system, and others, came into being. Furthermore, the JWST's observations are expected to provide vital data on the search for habitable planets beyond our own solar system. As astronomers discover more exoplanets, planets that orbit stars other than our Sun, JWST will help determine whether any of these distant worlds could potentially support life. The telescope's ability to analyze the atmospheres of these exoplanets will be key in determining whether they have the necessary conditions for life as we understand it. It's a step closer to answering one of the most profound questions humanity has ever asked: are we alone in the universe? But with all these capabilities, the JWST also brings with it a sense of awe and uncertainty. As we begin to receive data from the telescope, we are confronted with the possibility that the discoveries it makes may completely upend our understanding of the universe. Could the JWST reveal cosmic phenomena so strange, so far beyond our comprehension, that they force us to rethink the very laws of physics? Could it uncover evidence that challenges our most fundamental assumptions about the nature of reality? The prospect of such revelations fills the scientific community with both excitement and trepidation. Already, the first images from the JWST have stunned the world. These images, which show galaxies, nebulae, and star clusters in extraordinary detail, offer a breathtaking glimpse into the vastness and complexity of the universe. The colors, the textures, and the patterns that emerge from these images are not just beautiful, they are the raw data from which we will begin to understand the true nature of space and time. They remind us that we are on the cusp of a new era in our quest to unravel the mysteries of the cosmos. The James Webb Space Telescope is more than just a scientific instrument. It is a symbol of humanity's unyielding desire to understand the unknown. It is a testament to our ability to look beyond our planet, beyond our solar system, and into the farthest reaches of the universe. The discoveries that the JWST will continue to make in the coming years have the potential to change everything we know about the cosmos, and ourselves. And as we venture deeper into this cosmic enigma, we are reminded that the pursuit of knowledge is an endless journey, one that will always keep us looking toward the stars, searching for answers and wondering what lies beyond the horizon. When the James Webb Space Telescope, JWST, first sent back its images and data, it became clear that the universe had more secrets than we could have imagined. These revelations were not just stunning images of distant galaxies or nebulae. They were snapshots of the universe itself, unfolding before our eyes, answers to questions that have baffled scientists for centuries, but also new questions that arose with every discovery. What the JWST revealed was more than just the beauty of space. It showed us that the universe is far stranger and more complex than we ever thought possible. The first few images from the JWST captured the imagination of people around the world. They were stunning, yes, but more importantly, they were unprecedented. The telescope's ability to observe distant galaxies in infrared light opened up entire new vistas of discovery. It could peer through the cosmic dust and gas that had previously blocked our view, revealing galaxies and star systems in unparalleled detail. The clarity and depth of these images left even seasoned astronomers in awe, as if they were witnessing a new chapter in the book of cosmic exploration. One of the first discoveries that captivated the scientific community was the level of detail the JWST provided in its images of galaxies. These galaxies were often billions of light-years away, yet they appeared in extraordinary detail, their structures and individual stars visible in ways that had never been possible before. Some of these galaxies were so distant that they had formed only a few 100 million years after the Big Bang, offering a glimpse into the very earliest stages of the universe's evolution. This was a breakthrough moment in cosmology. For the first time, we could study galaxies in their infancy, long before they had evolved into the complex systems we see in the modern universe. The JWST's infrared capabilities also allowed it to peer into the hearts of star-forming regions, where new stars and planetary systems are born. Previously, these areas were hidden from our view by dense clouds of gas and dust, but the JWST could see right through them. What it revealed was nothing short of extraordinary. The telescope's ability to capture these star-forming regions in high detail gave scientists a new window into the processes that drive the birth of stars and planets. It was like watching the genesis of a star, seeing the very building blocks of matter come together in real time. This discovery had enormous implications for our understanding of stellar evolution, showing us exactly how the most fundamental elements of the universe are created. But the JWST did not just unveil distant galaxies or young stars, it also provided a glimpse into the mysteries of dark matter and dark energy. These two enigmatic forces make up most of the universe's mass and energy, yet we have little understanding of their true nature. With its incredibly sensitive instruments, the JWST began to observe the gravitational effects of dark matter, helping scientists map its distribution across vast cosmic structures. For the first time, we were able to see the faintest traces of dark matter, piecing together the cosmic puzzle in ways we never thought possible. In addition to uncovering the secrets of dark matter, the JWST provided new insights into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. By studying distant supernovae and the behavior of galaxies, the telescope was able to measure the rate of expansion with unprecedented accuracy. These measurements were crucial in refining our understanding of the cosmos, shedding light on one of the biggest unsolved mysteries of modern physics. Could dark energy be the key to understanding the universe's ultimate fate? Or is it a phenomenon that defies our current models of physics? The JWST's discoveries left these questions hanging in the air, tantalizingly close but still elusive. Perhaps the most thrilling aspect of the JWST's early discoveries, however, was its ability to directly observe exoplanets, planets outside our solar system. The search for exoplanets has been one of the most exciting areas of astronomy in recent years, but even the most advanced telescopes have struggled to detect these distant worlds. The JWST, with its high sensitivity to infrared light, was able to peer into the atmospheres of exoplanets in unprecedented detail. In doing so, it uncovered a wealth of new information about these distant worlds, including their chemical compositions, temperatures, and potential for habitability. One of the most exciting prospects of the JWST's exoplanet research is its potential to detect signs of life beyond Earth. By analyzing the chemical composition of exoplanet atmospheres, the telescope can search for biosignatures, substances that might indicate the presence of life. Could the atmosphere of a distant planet contain oxygen, methane, or other gases that might suggest the existence of life forms? The search for these signs of life is one of the most profound missions of the JWST, and the telescope's early results have been nothing short of groundbreaking. For the first time, scientists are able to study exoplanets in such detail that the possibility of finding life on another world feels closer than ever before. But as much as the JWST's discoveries have filled us with wonder, they have also led to new questions that are just as mysterious and tantalizing as the ones we've already answered. For example, the telescope's observations have revealed galaxies that seem to defy the conventional models of cosmic evolution. Some of these galaxies appear to have formed much earlier than previously thought, raising questions about how galaxies evolve and how they grow over time. What caused these early galaxies to form so quickly? And could the formation of galaxies happen in a way we've never considered before? These discoveries challenge our current understanding of the universe's history and force us to rethink how galaxies form, grow, and evolve. Another key discovery made by the JWST is the detection of strange and unexpected features in the cosmic background radiation. The universe's cosmic microwave background, CMB, is the faint afterglow of the Big Bang, a remnant of the moment when the universe was born. For decades, scientists have studied this radiation to learn more about the universe's earliest moments. But the JWST's observations revealed anomalies in the CMB, patterns that do not align with the predictions of current models. These anomalies suggest that there may be more to the history of the universe than we previously thought. Could these strange features be signs of hidden dimensions or alternate realities? The mysteries surrounding the CMB are far from solved, and the JWST has only just begun to explore these bizarre features in detail. Perhaps the most profound aspect of the JWST's discoveries, however, is the way they challenge our place in the universe. For centuries, humans have looked up at the stars and wondered if we are alone. The search for extraterrestrial life has been a central pursuit in science, philosophy, and even religion. But the discoveries made by the JWST have opened the door to the possibility that we are not the only intelligent beings in the cosmos. The telescope's observations of exoplanets, star systems, and the potential for life beyond Earth have brought us closer to answering one of humanity's most enduring questions. Are we alone in the universe? The discoveries of the JWST have already reshaped our understanding of the universe, but they are only the beginning. As the telescope continues to send back data, we will undoubtedly learn more about the fundamental nature of the cosmos. The discoveries made so far have shown us a universe that is far stranger and more complex than we ever imagined, filled with mysteries that will continue to captivate our imagination for generations to come. The JWST has given us a glimpse into the unknown, and with every new discovery, it brings us one step closer to unraveling the most profound secrets of the universe. Throughout history, the line between science and fiction has been a blurry one. What was once thought to be the realm of imagination, the stuff of science fiction, often finds itself in the realm of science fact. As our understanding of the universe has evolved, the distinction between these two realms has grown increasingly difficult to draw. The idea of alien life, intergalactic travel, time dilation, and other phenomena that once existed only in the pages of books and films has gradually moved into the territory of serious scientific inquiry. The James Webb Space Telescope, JWST, is at the forefront of this shift, presenting findings so extraordinary that they blur the line between what we know to be true and what once seemed impossible. One of the most profound ways in which science and fiction converge is through the discovery of exoplanets. For centuries, the idea of planets existing outside our solar system was relegated to the pages of science fiction novels. The possibility of alien worlds orbiting distant stars was a tantalizing concept, but one that seemed so far removed from reality that it hardly seemed worth consideration. Yet, over the last few decades, astronomers have confirmed the existence of thousands of exoplanets, many of which bear striking similarities to Earth. Some orbit in the habitable zone of their stars, where conditions might allow liquid water to exist, an essential ingredient for life as we know it. But it is not just the discovery of exoplanets that echoes the ideas once confined to fiction. The JWST's advanced capabilities have allowed scientists to analyze the atmospheres of these distant worlds in unprecedented detail. This has opened up the possibility of detecting biosignatures, gases or chemicals that could suggest the presence of life. As we study these distant planets, we begin to entertain the very real possibility that life exists elsewhere in the universe. What was once the plot of countless sci-fi novels is now on the verge of becoming scientific reality. Could the distant worlds discovered by JWST harbor life, or at least the conditions necessary for life to thrive? And if so, what does this mean for our place in the cosmos? Could we soon be on the verge of confirming the existence of extraterrestrial life, something humanity has pondered for centuries? The quest for extraterrestrial life is not the only area where science and fiction intersect. The concept of space travel and exploration has also been the stuff of science fiction for as long as we have dreamed of reaching the stars. While we have yet to achieve the interstellar travel portrayed in books and movies, the advent of the JWST and other space exploration initiatives has brought us closer than ever to understanding what lies beyond our own solar system. As we probe distant galaxies and stars, we are uncovering new information about the nature of the universe, the formation of planetary systems, and the potential for future human exploration of other worlds. For example, the JWST has already begun to observe distant galaxies and star systems that are billions of light-years away. These observations allow us to see galaxies as they appeared billions of years ago, offering a window into the early stages of the universe. What we are learning from these distant galaxies could have profound implications for our understanding of how galaxies form and evolve, and ultimately how our own galaxy, the Milky Way, came to be. The idea of peering back into the very beginning of time, of seeing the first stars, galaxies and black holes, might have once been a dream, but it is now a reality made possible by the advanced technology of the JWST. We are able to trace the cosmic origins of the universe, taking us closer to understanding the fundamental forces that govern it. But the implications of these discoveries go beyond merely expanding our scientific knowledge. The findings made by the JWST, and the mysteries they continue to reveal, raise fundamental questions about our place in the universe. What if we are not alone in the universe? What if the answers we find in these distant galaxies, or in the atmospheres of exoplanets, lead us to a truth so profound that it challenges the very fabric of human existence? The possibility that we might find evidence of life, or even intelligent civilizations, elsewhere in the cosmos has the potential to redefine our understanding of life and consciousness. If we are not alone, what does that mean for our own future? Are we a small, insignificant species on the outskirts of a vast, interconnected universe, or are we part of something much larger, a cosmic family that spans the stars? This sense of wonder and awe is not limited to the discovery of alien life or distant galaxies. The JWST also challenges our understanding of the fundamental nature of space and time. Through its observations, scientists are gaining new insights into the behavior of black holes, the nature of dark matter, and the enigmatic forces that drive the expansion of the universe. These revelations could very well lead to new theories of physics that challenge everything we thought we knew about the laws of nature. The existence of black holes, for instance, was once thought to be pure science fiction. The idea of an object so dense that nothing, not even light, could escape its gravitational pull was a concept straight out of fantasy. But today, black holes are a well-established aspect of our understanding of the universe. We know that they are the remnants of massive stars, collapsed under their own gravity, and that they play a crucial role in the evolution of galaxies. JWST's ability to observe these black holes in greater detail will undoubtedly provide us with new insights into their behavior, helping us unlock even more secrets about the nature of space and time. Similarly, the mysteries of dark matter and dark energy, once considered abstract concepts, have become central to our understanding of the universe's structure and fate. These invisible forces, responsible for much of the universe's mass and the accelerated expansion of space, remain largely mysterious. Yet, through the data provided by the JWST, scientists are beginning to piece together the puzzle of dark matter, attempting to understand its role in shaping the universe. The possibility that we are on the verge of unlocking the secrets of these fundamental forces brings science ever closer to the speculative realms of science fiction, where such forces were once seen as exotic and impossible. Even time itself, once thought to be a fixed and immutable aspect of reality, is being called into question. The JWST's ability to observe the universe as it was billions of years ago, at the dawn of time, has led to new theories about the nature of time, space, and the Big Bang. Could the universe have begun in a way that defies our current understanding of physics? Could time itself be more fluid, more malleable than we ever imagined? These are the kinds of questions that once occupied the minds of science fiction writers and philosophers, but now they are central to the work of cosmologists and physicists, as they attempt to unravel the deepest mysteries of the universe. The line between science and fiction has never been more porous. As we continue to make discoveries that challenge the boundaries of human knowledge, we find ourselves in a position where the impossible becomes possible, and the improbable becomes the new frontier. The JWST, with its groundbreaking observations, is pushing us closer to the point where the scientific and the fantastical converge, opening up new worlds of possibility and raising new questions that have the potential to alter our perception of reality. What was once the domain of fiction has become the realm of science, and with each new discovery, we are reminded of the vast, uncharted expanse of the universe that lies before us, waiting to be explored. The concept of time has long fascinated humanity. We experience it as linear, a steady march from past to present, with the future forever just out of reach. Yet, in the vastness of the cosmos, time does not flow in the same way. Here, time stretches and bends in ways that defy our understanding, especially when we peer deep into the universe's history. Through the eyes of the James Webb Space Telescope, JWST, we have begun to glimpse the universe as it was billions of years ago, providing us with a rare opportunity to look back in time and see the formation of galaxies, stars, and even the birth of the universe itself. This new ability to peer into the past is nothing short of revolutionary, offering a window into cosmic events that shape the very fabric of the cosmos as we know it. When we look into the night sky, we are not simply seeing the stars as they are today. In truth, we are looking back in time, seeing the light that left distant stars and galaxies billions of years ago. This is because light travels at a finite speed, meaning that the farther away an object is, the longer it takes for its light to reach us. When we observe a star that is, say, 1,000 light-years away, we are actually seeing the light it emitted 1,000 years ago. The same principle applies to galaxies, nebulae, and other distant cosmic objects. But the JWST allows us to look back in time in a way that no previous telescope could, giving us a much clearer, sharper view of the universe's past. One of the most profound ways in which the JWST has changed our understanding of time is through its ability to observe the earliest galaxies that formed after the Big Bang. The light from these galaxies has traveled for billions of years, and what we see today is a snapshot of a universe in its infancy. This is the very beginning of cosmic history, a time when the first stars were igniting, and the first galaxies were taking shape. In the distant past, the universe was a hot, dense soup of particles and energy. Over time, matter began to clump together under the influence of gravity, eventually forming the first stars and galaxies. But the details of this process and how exactly galaxies formed and evolved have remained largely a mystery, until now. The JWST's ability to observe these early galaxies is groundbreaking. By looking at galaxies that are billions of light-years away, the telescope can capture images of galaxies that formed only a few 100 million years after the Big Bang. This is the cosmic dawn, the time when the first structures in the universe began to emerge from the primordial fog of particles and radiation. The images sent back by the JWST have revealed galaxies that are strikingly different from the ones we see today. These early galaxies were smaller, less mature, and often more chaotic than the galaxies of today. Some of them were formed in just a few 100 million years, far faster than scientists had previously thought possible. This rapid formation of galaxies in the early universe raises important questions about the processes that govern galaxy formation and whether our current models of cosmic evolution need to be adjusted. One of the most remarkable aspects of the JWST's ability to peer back in time is its ability to detect the earliest stages of star formation. When we look at distant star-forming regions, we are not just seeing the stars as they are today, we are seeing them as they were when they were born, still in the process of forming from clouds of gas and dust. This allows us to study the very processes that lead to the birth of stars and planets. The formation of stars is a key process in the evolution of the universe, as stars are the building blocks for galaxies and planetary systems. By observing how stars form in these distant galaxies, the JWST is helping us understand how stars and planetary systems like our own came into being. But looking back in time doesn't just mean observing distant galaxies and stars. The JWST also provides us with a glimpse into the earliest moments of the universe itself. The first few moments after the Big Bang were a chaotic, violent period when the universe was incredibly hot and dense. As the universe expanded, it cooled and the first atoms, primarily hydrogen and helium, formed. This is when the first light began to travel across the universe, a light that would eventually reach us as the cosmic microwave background (CMB) radiation. The JWST cannot directly observe the Big Bang itself, but it is helping to fill in the gaps in our understanding of this early period in the universe's history. By studying the oldest galaxies and the faintest light that has traveled through space, the JWST is providing crucial data that helps us understand how the universe evolved from the moment of the Big Bang to the vast, structured cosmos we see today. What the JWST reveals about the earliest galaxies and stars raises fundamental questions about the nature of time and the universe's origin. How did the first galaxies form so quickly after the Big Bang? What processes allowed these small, early galaxies to grow into the massive galaxies we see today? And what does this mean for our understanding of the universe's evolution over billions of years? These are questions that have long eluded scientists, but with the help of the JWST, we are now closer than ever to finding answers. But the ability to look back in time also brings with it an unsettling realization. The further back we look, the more we realize how little we truly understand. The early universe was a wild, chaotic place, and the processes that shaped it were vastly different from anything we see today. For example, the first galaxies were smaller and more irregularly shaped than those in the modern universe. They were also much more active, with high rates of star formation and violent interactions with other galaxies. This raises questions about the role of cosmic events like galaxy collisions and supernova explosions in the formation of galaxies and the growth of stars. The universe we see today is the result of billions of years of evolution, but much of that evolution remains shrouded in mystery. As the JWST continues to send back data, it is becoming increasingly clear that our current models of cosmic evolution need to be adjusted. The early universe was far more complex and dynamic than we previously thought. Galaxies and stars formed more rapidly than we expected, and the processes that led to their formation were more chaotic and unpredictable. This is both exciting and humbling for scientists, as it suggests that our understanding of the universe is still in its infancy. Each new discovery made by the JWST opens up new questions and challenges our preconceived notions of how the universe works. Peering back in time, the JWST allows us to witness the universe's first steps. It is a powerful reminder of how little we truly know about the cosmos, even as we continue to uncover new details. The telescope's observations provide us with a glimpse into a time when the universe was young, full of potential and mystery. But they also remind us of the vastness of the unknown. The farther back we look, the more complex the universe becomes, and the more we realize that our journey to understand it has only just begun. In this way, the JWST's ability to look back in time is not just a tool for exploring the past, it is a tool for reshaping our future understanding of the universe and our place within it. The more we look, the more we uncover, and the more we realize that the universe's story is far from finished. It is a story still unfolding, and we are only beginning to witness its first chapters. For centuries, humanity has gazed at the stars, pondering one of the most profound questions in existence. Are we alone in the universe? The question of extraterrestrial life has sparked curiosity, speculation, and imagination across cultures, religions, and scientific disciplines. It has inspired countless myths, stories, and scientific theories, but despite our best efforts, we have found no definitive evidence of life beyond Earth. Yet, the search for life continues to be one of the most compelling pursuits of modern science, and the launch of the James Webb Space Telescope (JWST) has opened new avenues for exploring this age-old question. The JWST is a scientific marvel that has revolutionized our understanding of the cosmos, not only by capturing breathtaking images of distant galaxies and stars, but also by providing the tools to explore the possibility of life elsewhere in the universe. With its unparalleled sensitivity to infrared light, the JWST is able to study the atmospheres of exoplanets in unprecedented detail, offering scientists a chance to search for signs of life far beyond our solar system. It is perhaps the most powerful tool ever created for answering the question, could there be life out there waiting to be discovered? The hunt for life outside Earth is built upon the idea that, given the vastness of the universe, it seems statistically improbable that Earth is the only planet to harbor life. The universe is so vast that it contains billions of stars, each with its own planetary system. Many of these stars are similar to our Sun, and many of their planets orbit in the habitable zone. the region around a star where conditions might be right for liquid water to exist. Water is considered a crucial ingredient for life as we know it, and the presence of liquid water on a planet is one of the key factors in determining whether a planet could support life. For years, astronomers have focused on detecting exoplanets, planets that orbit stars outside our solar system. Thousands of exoplanets have been discovered in the last few decades, some of which appear to be in the habitable zone of their stars. However, the real challenge has been determining whether these exoplanets have the necessary conditions to support life. Detecting life on exoplanets, or even evidence of its potential, requires more than just discovering planets in the right location. Scientists must also study the chemical composition of these planets, looking for signs of an atmosphere that could sustain life. This is where the JWST comes in. One of its most groundbreaking capabilities is its ability to study the atmospheres of distant exoplanets. The telescope's advanced infrared instruments can detect the chemical makeup of these atmospheres, allowing scientists to look for the presence of certain gases that could indicate biological activity. For example, the presence of oxygen, methane, or carbon dioxide, gases that are often associated with life on Earth, could be an important clue in the search for extraterrestrial life. These gases can be produced by biological processes, and their detection in an exoplanet's atmosphere could suggest that life exists, or at least once existed, on that planet. The JWST's ability to detect biosignatures is a game-changer. Previous telescopes, including the Hubble Space Telescope, have been able to study exoplanet atmospheres, but the JWST's advanced instruments can analyze these atmospheres with much greater precision. It can detect even the faintest traces of gases in the atmospheres of exoplanets that are light-years away. This allows scientists to conduct a more thorough search for signs of life, even in planets that are far beyond our reach. In fact, the ability to study the atmospheres of exoplanets is one of the most exciting aspects of the JWST's mission. For the first time, we are able to explore the potential for life on distant worlds with a level of detail that was once unimaginable. But the search for life is not limited to just looking for biosignatures in exoplanet atmospheres. The JWST also plays a critical role in studying the conditions that might support life. By observing the chemical composition of exoplanet atmospheres, scientists can determine whether they contain the right balance of gases, pressure, and temperature to support life. In addition to water, scientists also look for the presence of key elements such as nitrogen, carbon, and sulfur, which are essential for life as we know it. If an exoplanet's atmosphere contains the right combination of these elements, it could suggest that the planet has the necessary conditions to support life. One of the most exciting developments in the search for life is the discovery of Earth-like exoplanets. These planets, which are roughly the same size as Earth and orbit within their star's habitable zone, are prime candidates for the search for life. The JWST's ability to study these planets in detail gives scientists the best chance yet of finding a world that could harbor life. Some of these planets may have oceans, atmospheres, and even weather systems similar to our own, offering the possibility that they could support life forms. While we have yet to find definitive evidence of life on these exoplanets, the mere existence of these worlds is a tantalizing hint that life elsewhere in the universe may be more common than we think. But what if we are looking for the wrong signs? What if life exists in forms that we don't recognize or understand? This is one of the most intriguing questions in the search for extraterrestrial life. The quest to find life is often based on the assumption that life elsewhere in the universe will be similar to life on Earth. We search for water, oxygen, and methane because these are the conditions that support life as we know it. But what if life exists in forms that are completely different from anything we have ever imagined? What if there are life forms that don't rely on water or oxygen, or that live in environments that are hostile to us? Could there be life on planets that are far hotter, colder, or more extreme than Earth? This possibility has led to some of the most speculative theories about life beyond Earth. For example, some scientists have suggested that life could exist in the clouds of Venus, where the temperature and pressure are extreme, yet certain chemical processes could potentially support life. Others have hypothesized that life could exist on moons like Europa or Enceladus, where subsurface oceans might provide the conditions necessary for life to thrive. The JWST, with its advanced instruments, will be able to study these moons and planets in greater detail than ever before, helping scientists explore these extreme environments and determine if they could support life in some form. As we continue to explore the possibility of life beyond Earth, the JWST will be an invaluable tool in the search for extraterrestrial life. It will not only help us detect signs of life on distant planets, but it will also deepen our understanding of the conditions that might support life in the first place. The search for life is one of the most profound and exciting pursuits in science, and the JWST's discoveries will play a central role in shaping our understanding of the universe and our place within it. But as we search for life, we must also confront a sobering possibility. What if we are alone? The absence of signs of life on the exoplanets we study could be a stark reminder of how rare and fragile life might be. The discovery that Earth is the only planet in the universe to support life would be a humbling revelation, one that challenges our assumptions about the nature of existence. Yet, even in the face of this uncertainty, the search for life continues to inspire and drive us, because the question of whether we are alone is one of the most fundamental and profound questions humanity can ask. The hunt for life beyond Earth is not just a scientific endeavor, it is a philosophical one too. It challenges us to rethink our place in the universe, to question what it means to be alive, and to consider the implications of discovering that we are not alone. Whether or not we find life on other planets, the search itself deepens our understanding of what it means to be human, to exist in such an immense, awe-inspiring universe. As the JWST continues its mission, it promises to bring us closer to answering this question, but the answers it uncovers may be far more complex, and more humbling, than we could have ever imagined. In the vast expanse of the universe, there are forces at play that we cannot see, touch, or even fully comprehend. These mysterious forces, dark matter and dark energy, make up approximately 95% of the universe, yet we know almost nothing about them. Despite their dominance in the cosmos, they remain invisible and elusive, hiding from our detection and continuing to defy the limits of human understanding. The James Webb Space Telescope, JWST, with its extraordinary capabilities, is helping scientists unlock the secrets of these dark forces, and in doing so, it is transforming our understanding of the very nature of reality. Dark matter, which constitutes about 27% of the universe, is an invisible substance that doesn't emit, absorb, or reflect light, making it undetectable by traditional means. Yet, despite its invisibility, we know dark matter exists because of its gravitational effects on visible matter. Galaxies, for example, spin much faster than they should based on the amount of visible matter present in them. Without dark matter's gravitational pull, these galaxies would simply fly apart. This gravitational influence extends to larger cosmic structures, such as galaxy clusters, where dark matter helps hold the clusters together despite the apparent absence of enough visible mass to do so. For decades, scientists have been trying to understand the true nature of dark matter. Many have speculated that dark matter is made up of exotic particles, which, although they do not interact with light or other forms of electromagnetic radiation, could have mass and therefore exert gravitational influence. The leading candidates for dark matter particles are known as WIMPs, weakly interacting massive particles, which could be detected through their interaction with ordinary matter. However, despite years of searching, no direct detection of dark matter has been made. This is where the JWST comes into play, offering a new opportunity to study dark matter through its gravitational effects. One of the most significant ways that JWST can help us learn about dark matter is through its ability to observe distant galaxies and galaxy clusters. By studying the way light from distant objects bends as it passes through a galaxy cluster, an effect known as gravitational lensing, scientists can map the distribution of dark matter. This is because dark matter has mass, and its gravitational influence bends the path of light, much like a magnifying glass bends light. The JWST's unprecedented ability to capture high-resolution images of galaxy clusters will allow scientists to more precisely map the locations and distribution of dark matter in the universe. These observations could help to answer key questions about the nature of dark matter, including what it is made of, how it interacts with other forms of matter, and whether there are different types of dark matter spread throughout the cosmos. While dark matter is mysterious, dark energy is even more perplexing. Dark energy is an even more dominant force, comprising about 68% of the universe, and is responsible for the accelerated expansion of the cosmos. Since its discovery in the late 1990s, dark energy has baffled scientists. It behaves in a way that defies all of our current understanding of gravity and forces. Rather than slowing the expansion of the universe due to gravitational pull, dark energy seems to be pushing the universe apart at an ever-increasing rate. This discovery led to one of the most significant paradigm shifts in cosmology, as it suggested that the universe's fate is not one of gradual contraction or steady expansion, but rather an accelerating and unpredictable growth driven by an invisible force. The true nature of dark energy remains one of the most pressing questions in modern physics. Some theories suggest that dark energy is a property of space itself, something known as the cosmological constant. This would imply that the energy density of space is constant, regardless of the expansion of the universe. Other theories propose that dark energy could be a dynamic field, something that changes over time and might even evolve as the universe ages. The JWST is perfectly poised to help answer this question by observing the rate of the universe's expansion with unprecedented accuracy. By studying distant supernovae, exploding stars that serve as standard candles for measuring cosmic distances, and mapping the large-scale structure of the universe, JWST will help refine our understanding of how dark energy is influencing the cosmos. One of the most exciting aspects of the JWST's potential in studying dark energy is its ability to observe the earliest stages of the universe's expansion. The telescope's infrared capabilities allow it to see galaxies and structures that are billions of light-years away, looking back in time to when the universe was much younger. By comparing the expansion of the universe at different points in time, scientists hope to learn more about how dark energy has evolved and how it may continue to shape the universe's fate. Will dark energy eventually cause the universe to expand forever, growing colder and more diffuse? Or is there a possibility that dark energy will change over time, leading to a different cosmic outcome? These are questions that the JWST is uniquely equipped to help answer. Another intriguing possibility raised by dark energy is its potential connection to the fundamental structure of the universe. Some scientists have speculated that dark energy could be related to quantum fluctuations in empty space, a phenomenon predicted by quantum mechanics. These fluctuations could give rise to the energy that drives the universe's expansion. The JWST's ability to probe deep into the universe's history could help us understand whether this connection between dark energy and quantum mechanics is real, or if dark energy operates according to principles that are completely different from anything we've imagined. While dark matter and dark energy are two of the greatest mysteries in modern physics, their study is not just an intellectual pursuit. It has profound implications for our understanding of the universe and its future. The discovery of dark matter and dark energy reshaped our understanding of the cosmos, revealing that the visible universe, the stars, galaxies, and planets we can observe, constitutes only a small fraction of what exists. These invisible forces are what drive the cosmos, shaping its expansion, its structure, and its ultimate fate. Understanding them is key to answering some of the most profound questions in science. What is the true nature of the universe? How did it come to be? And what will its future hold? The JWST is offering us an unprecedented opportunity to study dark matter and dark energy in ways we never thought possible. Through its ability to observe distant galaxies, galaxy clusters, and the large-scale structure of the universe, we are beginning to unravel the secrets of these elusive forces. While much remains unknown, the discoveries that the JWST will continue to make in the coming years will undoubtedly reshape our understanding of the universe, providing us with a deeper, more comprehensive view of the cosmos and the hidden forces that govern it. As we continue to explore the mysteries of dark matter and dark energy, we are reminded of the vastness of the unknown. Despite the incredible progress we have made in understanding the universe, we are still only scratching the surface. Dark matter and dark energy may remain mysterious for years to come, but with the JWST, we are now better equipped than ever to unravel their secrets and, perhaps, to unlock the most profound mysteries of the universe itself. When we look at the night sky, we are accustomed to seeing stars, planets, galaxies, and nebulae, all shining in the vast emptiness of space. These are the objects that we can observe with our eyes, or through telescopes that capture light across different wavelengths. However, there is an entire universe beyond the visible, a universe that remains hidden, lurking just out of reach. This unseen universe consists of things that cannot be directly observed because they do not emit, reflect, or absorb light in any form we can detect. Yet, these invisible forces and substances shape the cosmos in profound ways, influencing the formation of galaxies, stars, and planetary systems, as well as the overall structure of the universe itself. At the heart of this unseen universe are dark matter and dark energy, two of the most enigmatic phenomena in modern astrophysics. These forces are invisible to traditional telescopes and remain undetectable through conventional means, yet they account for approximately 95% of the universe's total mass energy content. Dark matter alone makes up about 27% of the universe, and dark energy comprises around 68%. The remaining 5% consists of the matter and energy that we can observe directly, the stars, planets, and galaxies that make up the visible universe. This stark division between the seen and unseen aspects of the cosmos raises profound questions. What exactly is dark matter and dark energy? How do they affect the universe? And perhaps most intriguingly, why can't we see them? One of the most perplexing aspects of dark matter is that, while it does not emit light or any form of electromagnetic radiation, we can infer its existence by observing its gravitational effects. The way galaxies rotate, for example, suggests that they contain far more mass than can be accounted for by the visible stars and gas alone. Without the additional gravitational pull from dark matter, these galaxies would fly apart. Likewise, the way galaxy clusters behave, how they interact with one another and how light from more distant objects bends around them, points to the presence of large quantities of unseen mass. It is as though the universe is revealing itself to us through its invisible scaffolding. And yet, despite all of these clues, the true nature of dark matter remains elusive. Some scientists believe it might be composed of exotic particles such as WIMPs, weakly interacting massive particles, that don't interact with light, while others are exploring alternative explanations. The JWST, with its advanced infrared capabilities, promises to provide crucial insights into the nature of dark matter. While it cannot detect dark matter directly, the telescope can study the way light interacts with massive cosmic structures, such as galaxy clusters. One of the most powerful tools for studying dark matter is gravitational lensing, the phenomenon by which light from distant objects is bent and distorted by the gravitational pull of a massive object, such as a galaxy cluster. This bending of light allows scientists to map the distribution of mass within a galaxy cluster, including the hidden dark matter. The JWST's ability to capture high-resolution images of galaxy clusters will allow astronomers to refine their understanding of dark matter's role in shaping the universe, providing valuable data on where and how dark matter is distributed. But dark matter is not the only invisible force shaping the universe. Dark energy, the mysterious force that is causing the accelerated expansion of the cosmos, is even more enigmatic. Unlike dark matter, which has mass and exerts a gravitational pull, dark energy seems to have a repulsive effect, pushing galaxies apart and accelerating the expansion of the universe. The discovery of dark energy in the late 1990s, through observations of distant supernovae, shocked the scientific community. It was a finding that upended our understanding of the universe's fate, suggesting that the cosmos would not eventually collapse back in on itself as had been previously thought, but rather continue expanding forever. While dark energy is even more difficult to study than dark matter, the JWST's ability to observe distant galaxies and supernovae could provide the key to unlocking its mysteries. By studying the rate at which galaxies are receding from us, astronomers can measure the acceleration of the universe's expansion. This allows scientists to map the influence of dark energy on the cosmos over time, offering new clues about its nature and its role in the universe's evolution. The JWST's ability to look back in time, observing galaxies and supernovae as they were billions of years ago, will provide a deeper understanding of how dark energy has affected the expansion of the universe since its inception. While dark matter and dark energy are the most significant invisible forces in the universe, there are other phenomena that remain unseen yet play critical roles in the cosmos. One such force is gravity. Although gravity is the force that governs the motion of galaxies, stars, and planets, it is a force that we cannot directly observe. We feel gravity's effects on Earth every day, but we can never see the force itself. However, through the lens of general relativity, scientists have developed a deep understanding of how gravity works on both large and small scales. The bending of spacetime around massive objects, for example, is a phenomenon that is invisible to the naked eye but can be detected by the way light and matter behave near these objects. The JWST, with its powerful instruments, will provide a new way of observing the effects of gravity on the most extreme cosmic environments, such as near black holes or in the early universe, offering new insights into the fundamental nature of gravity and its role in shaping the cosmos. Another unseen phenomenon that the JWST will help us explore is the role of cosmic dust in the universe. Cosmic dust is composed of tiny particles of matter that are scattered throughout space, and while it is invisible to the naked eye, it plays a crucial role in the formation of stars, planets, and galaxies. In fact, the dust in galaxies is responsible for obscuring our view of many distant objects. While dust can block the light from stars and galaxies in visible wavelengths, it can be studied through infrared light, which passes through dust clouds with much less attenuation. The JWST's ability to observe in the infrared spectrum allows it to peer through these cosmic dust clouds, offering new insights into star formation, the evolution of galaxies, and the birth of planetary systems. But perhaps the most profound aspect of the unseen universe is the way it challenges our understanding of reality itself. The more we learn about the invisible forces and phenomena that shape the cosmos, the more we realize how much there is still to discover. The universe is not a static, unchanging entity but a dynamic, complex system that is shaped by forces beyond our comprehension. The JWST, with its ability to observe the most distant and ancient regions of space, is helping to uncover these hidden aspects of the universe, providing us with a deeper understanding of the cosmos and our place within it. In a sense, the invisible universe is a reflection of our own limitations. As we strive to understand the vast and mysterious cosmos, we are confronted with the realization that there is so much more beyond our reach. But the quest to uncover the unseen, to look beyond the limits of our perception, is what drives scientific inquiry and exploration. With each new discovery made by the JWST, we are forced to confront the vastness of the unknown and expand the boundaries of our knowledge. And in doing so, we are uncovering the hidden forces that govern the universe, forces that, while invisible, are the very fabric of reality itself. As we peer deeper into the cosmos, uncovering the secrets of distant galaxies, stars, and exoplanets, we are constantly reminded of a staggering truth. No matter how far we reach, there is always more beyond our sight. The observable universe, everything we can detect through telescopes, instruments, and other means of observation, is vast beyond comprehension. It stretches over 93 billion light-years in diameter, containing hundreds of billions of galaxies, each with billions of stars. Yet, despite its enormity, this observable universe is only a small fraction of what we believe exists in the cosmos. Beyond the limits of what we can see lies the infinite unknown, a region of space that we cannot access, observe, or even begin to understand fully. This unobservable part of the universe is one of the most profound mysteries in cosmology, and the more we learn about the observable universe, the more we are reminded of the limitations of our knowledge. At the core of this mystery lies the question of what lies beyond the observable universe. We know that the universe began with the Big Bang around 13.8 billion years ago, and that since then, it has been expanding outward, carrying galaxies and all matter along with it. The expansion of the universe has not only caused the distances between galaxies to grow, but it has also stretched the very fabric of spacetime itself. This means that the farther away we look, the farther in time we are looking as well. Light from the most distant galaxies has taken billions of years to reach us, offering us a snapshot of the universe's early moments. But the further we look, the less we can see, as light from objects beyond a certain distance has not yet had time to reach us. This region, beyond the cosmic horizon, is the unobservable universe, and it is a place of profound mystery. The limits of the observable universe are determined by the speed of light and the finite time since the Big Bang. Because the universe has been expanding since its inception, there are regions of space that are now so far away from us that the light emitted from them has not had enough time to reach us. This means that there are parts of the universe that we will never be able to observe directly. The light from these distant regions may never reach Earth, not because it has been blocked or obscured by some barrier, but because the space between us and those regions has expanded too quickly for the light to ever catch up. These regions lie beyond the cosmic light horizon, which marks the limit of what we can see. This raises the question, what is beyond the observable universe? Is the universe infinite, stretching endlessly in all directions, or does it have some boundary? If the universe is infinite, then it could contain an unimaginable number of galaxies, stars, and planets, many of which might be very different from those we observe within our own corner of the cosmos. On the other hand, if the universe has an edge or boundary, what lies beyond it? Some cosmologists have proposed that the universe might be finite but unbounded, meaning that it has no edge but is still limited in size. This concept is difficult to grasp, as we tend to think of space as something that must have an edge or a boundary, but in the context of the universe, it is possible that space itself is curved, and that if you traveled far enough in one direction, you would eventually return to where you started, like traveling around the surface of a sphere. This theory is one of the many ways scientists are attempting to conceptualize the vast, mysterious space beyond what we can observe. Another theory that has emerged in recent years is the idea of a multiverse, an infinite collection of universes, each with its own set of physical laws and constants. According to this theory, our observable universe is just one of many that exist in a vast cosmic landscape. These universes might differ in terms of their fundamental properties, such as the strength of gravity, the mass of particles, or the number of dimensions of space. Some multiverse theories suggest that new universes are constantly being created in a process called cosmic inflation, where regions of spacetime expand rapidly, creating new bubbles of space that evolve into their own separate universes. This concept of the multiverse raises profound questions about the nature of reality itself. If the multiverse theory is correct, it could mean that everything we know, The laws of physics, the constants of nature, the very existence of our universe, might be just one realization of a much broader cosmic possibility. For now, the multiverse remains a speculative idea, and there is no direct evidence to support it. However, some physicists are hopeful that future advancements in observational technology, including the JWST, may provide indirect evidence that could shed light on the existence of other universes. One approach is to look for signatures of other universes in the cosmic microwave background (CMB), the faint afterglow of the Big Bang. Some theories of the multiverse suggest that interactions between different universes could leave detectable traces in the CMB, such as unusual patterns or anomalies in the data. While this is still a speculative area of research, the JWST's ability to probe the earliest stages of the universe and the fine details of the CMB could potentially provide new clues about the broader structure of reality. In addition to the possibility of a multiverse, there are other hypotheses about the nature of the unobservable universe. One such idea is the concept of parallel universes, in which different versions of reality coexist alongside our own, with different outcomes or histories. This idea is closely related to the many worlds interpretation of quantum mechanics, which suggests that every quantum event, every measurement, every particle interaction, could lead to the creation of a separate universe. Each universe in the many worlds interpretation would represent a different possible outcome of a quantum event, with an infinite number of parallel universes branching off from each decision point. While this theory has not been proven, it is an intriguing possibility that challenges our understanding of time, space, and reality itself. Even if we never discover direct evidence of other universes or the true nature of the unobservable universe, the mere existence of this cosmic unknown raises important philosophical and scientific questions. What does it mean for us to live in a universe that may be far larger, far more complex, and far more mysterious than we can even imagine? How do we come to terms with the limits of our knowledge and the realization that there may be things out there that we will never be able to see or understand? For many, this cosmic uncertainty is a humbling reminder of the vastness of the universe and our small place within it. The search for answers to these questions is a driving force behind modern cosmology, and while we may never have all the answers, the journey of exploration and discovery is, in itself, one of humanity's greatest endeavors. The JWST, with its advanced technology and unprecedented ability to peer deep into the universe, is providing us with the tools to probe the very edges of the observable universe and beyond. Although there are limits to what we can know and understand, each new discovery made by the telescope brings us closer to unlocking the secrets of the cosmos. Whether we are uncovering the details of distant galaxies, studying the formation of stars, or searching for signs of life, the quest to understand what lies beyond the observable universe will continue to shape our understanding of the cosmos for generations to come. The fate of the universe is one of the most profound and captivating questions in cosmology. For centuries, we have wondered about the ultimate destiny of the cosmos. Will it continue expanding forever, eventually cooling into a dark and lifeless void? Or will it collapse in on itself, ending in a cataclysmic Big Crunch? As our understanding of the universe has evolved, so too has our comprehension of how the cosmos might end. The discovery of dark energy in particular has drastically changed our view of the universe's fate. What was once thought to be a universe that might eventually slow and contract is now understood to be in the midst of an accelerated expansion, a process driven by the mysterious force of dark energy. One of the most widely accepted theories about the fate of the universe is the concept of heat death. As the universe expands, galaxies and stars will drift farther apart, and the universe will grow colder and more diffuse. Over time, stars will burn out, and black holes will slowly evaporate through a process known as Hawking radiation. As the universe ages, the amount of usable energy will decrease, and the cosmos will eventually reach a state of maximum entropy, where no more work can be done, and all matter and energy are evenly distributed across space. This heat death scenario is one in which the universe becomes a cold, dark, and desolate place, its once vibrant galaxies and stars reduced to faint remnants in an ever-expanding void. Another possible end to the universe is the Big Freeze, a scenario in which the universe continues to expand at an accelerating rate due to dark energy. As galaxies move farther apart, stars will burn out, and the universe will eventually reach a state of isolation. The gravitational pull between objects will weaken, and the cosmos will become increasingly sparse, with individual stars and planets drifting in isolation. Over an unimaginable span of time, the universe could become a vast, dark expanse with no light, no heat, and no life. This end is not a sudden event but rather a gradual process that unfolds over trillions of years, eventually leading to a universe that is eerily silent and devoid of activity. The JWST, with its ability to observe the most distant galaxies and the oldest light in the universe, is helping to illuminate the story of the cosmos expansion. By studying the rate of expansion and the influence of dark energy, astronomers can refine their models of the universe's fate. The telescope's unprecedented power to capture images of galaxies at various stages of development will provide valuable data on how cosmic structures form, evolve, and ultimately decay. The answers that the JWST uncovers will not only reveal the past and present of the universe but will also give us a clearer picture of what lies ahead in the distant future. The question of how life began is one of the oldest and most profound mysteries in science, philosophy, and human curiosity. From ancient civilizations gazing up at the stars to modern-day researchers using powerful telescopes like the James Webb Space Telescope, JWST, humanity has been relentlessly searching for answers to the question, how did life arise from the cold, barren cosmos? The origins of life, on Earth and beyond, are intricately linked to the cosmos itself, and understanding where we come from, how our existence emerged from a swirling sea of atoms, molecules, and stars, is central to our quest for knowledge. Life as we know it is a complex web of molecules, interactions, and energy. It thrives in environments that possess the right ingredients: water, organic molecules, and energy. But these essential ingredients don't exist in a vacuum. They were forged in the hearts of stars, billions of years ago, during the process of stellar nucleosynthesis. When stars like our Sun form, they begin to fuse lighter elements, like hydrogen and helium, into heavier elements such as carbon, nitrogen, and oxygen. These elements are the building blocks of life. Over billions of years, as stars die and explode in supernovae, they spread these essential elements throughout the universe, seeding the cosmos with the very building blocks that would one day come together to create life. One of the most compelling discoveries of modern astronomy is the recognition that the ingredients for life are not exclusive to Earth. Across the universe, scientists have found a remarkable diversity of organic molecules, amino acids, sugars, and even complex hydrocarbons, on comets, asteroids, and in the interstellar medium. These molecules are the fundamental components from which life on Earth is built, and their presence in distant regions of space suggests that the ingredients for life may be common across the universe. With the help of advanced telescopes like the JWST, scientists are now able to detect these organic molecules in distant star-forming regions, where the raw materials for life are being created in real time. These findings raise a tantalizing possibility. Life, or at least the precursors to life, may not be unique to our planet. Could life have emerged elsewhere in the universe, in other corners of the cosmos where the right conditions exist? One of the key steps in the origin of life on Earth was the formation of complex organic molecules capable of self-replication. The famous Miller-Urey experiment in the 1950s demonstrated that, under the right conditions, simple molecules like methane, ammonia, and hydrogen could react to form amino acids, the building blocks of proteins. This experiment provided the first tangible evidence that the basic ingredients for life could be synthesized under conditions thought to resemble those of the early Earth. However, while this experiment demonstrated the plausibility of prebiotic chemistry, it did not answer the most profound question: how did these simple molecules evolve into the first living organisms? How did life transition from being a collection of molecules to a self-sustaining, self-replicating system? The transition from chemistry to biology, from the inanimate to the living, is the most challenging part of the origin of life story. Scientists have proposed many theories to explain this leap, but the exact process remains unclear. One hypothesis is that life began in deep-sea hydrothermal vents, where heat and minerals from the Earth's interior could have provided the energy necessary to drive chemical reactions. These vents, rich in compounds like methane and hydrogen sulfide, create an environment where the ingredients for life could have come together to form the first simple cells. This theory is supported by the discovery of extremophiles, organisms that can survive in extreme conditions like deep-sea vents, acidic hot springs, and even the frozen tundra. The existence of these organisms suggests that life may be far more adaptable and resilient than we once thought, able to thrive in environments that were previously considered hostile to life. Another compelling theory is that life may have originated from molecules that were brought to Earth by comets, asteroids, or meteors. This idea, known as panspermia, posits that the seeds of life could have traveled through space, carried on celestial objects that collided with Earth. The idea that life could have been seeded across the universe is both humbling and awe-inspiring, suggesting that life on Earth may not be an isolated phenomenon, but part of a larger cosmic pattern. The discovery of organic molecules on comets and in interstellar space lends credence to this theory, offering a tantalizing possibility that life, or at least the building blocks of life, might be common throughout the cosmos. As we search for the origins of life on Earth, the search for life elsewhere in the universe becomes equally important. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up an entirely new frontier in the search for extraterrestrial life. Thousands of exoplanets have now been identified, many of which lie in the habitable zone of their stars, where conditions might be just right for liquid water to exist. Water, of course, is one of the key ingredients for life as we know it. But water alone is not enough. For life to emerge, the right combination of chemicals, energy, and time is needed. The question, then, is not just whether other planets have water, but whether they also have the other essential ingredients for life. The JWST, with its ability to observe distant exoplanets in unprecedented detail, will play a critical role in this search. One of the telescope's primary objectives is to analyze the atmospheres of exoplanets, searching for signs of habitability or even the presence of life. By studying the chemical composition of exoplanet atmospheres, scientists can look for biosignatures, chemical imbalances or patterns that suggest the presence of biological activity. For example, the presence of oxygen or methane in an exoplanet's atmosphere, in the right quantities, could indicate that life is at work. These gases are typically produced by biological processes, and their presence in an atmosphere could be a strong indicator that life is present, or at least that the conditions for life are favorable. The potential for discovering life beyond Earth is an idea that has captivated the human imagination for centuries. From ancient myths about alien gods to modern-day speculation about intelligent extraterrestrials, the question of life beyond Earth is one of the most profound and exciting topics in science. As we develop the technology to explore distant planets and moons, we are beginning to realize that life may not be as rare or unique as we once thought. The universe, with its vast expanse and diverse environments, may be teeming with life, both similar to ours and vastly different from anything we can imagine. Whether in the form of microbial life beneath the icy crusts of moons like Europa or Enceladus, or in the form of complex organisms on distant exoplanets, the search for life elsewhere is rapidly becoming one of the most exciting frontiers of modern science. At the same time, the study of the origin of life on Earth provides valuable insights into the conditions that make life possible. By understanding how life began on our planet, we can better understand how it might arise elsewhere. Could life emerge in places we never imagined, on planets without water or in environments vastly different from Earth? The more we learn about the origins of life, the more we realize how little we truly understand. The process is likely far more complex, mysterious, and interconnected than we ever imagined. It is a process that is not just about chemistry or biology, but about the interplay between the elements of the universe, stars, planets, and the fundamental forces that govern them. Ultimately, the search for the origin of life is a search for our place in the cosmos. It is a search to understand who we are, where we come from, and whether we are alone in the universe. It is a quest that connects us not only to our planet, but to the stars and the galaxies that surround us. As we continue to unravel the mysteries of life's origins, we are reminded of the profound interconnectedness of the universe, and the remarkable chance that brought life into being on our own planet. And perhaps as we look beyond our own world, we will find that life, whether in its simplest or most complex form, exists beyond the limits of our imagination, waiting to be discovered in the infinite expanse of the cosmos. In the vastness of the cosmos, where billions of stars and planets reside, it seems almost unimaginable that Earth is the only place where life has evolved. With so many potentially habitable worlds scattered across the universe, the question arises: why haven't we found any signs of intelligent extraterrestrial life? This question is known as the Fermi paradox, named after the renowned physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox presents a profound mystery. Given the seemingly high probability of life elsewhere in the universe, why do we remain so alone? The Fermi paradox is rooted in the mathematical possibility of life elsewhere. The Milky Way galaxy alone contains over 100 billion stars, many of which have planets in the habitable zone, where conditions could support liquid water, the key ingredient for life. If life arose on Earth under the right conditions, it stands to reason that similar conditions might exist on countless other planets. Even if only a small fraction of these planets host intelligent life, the sheer number of potential civilizations should make the universe seem teeming with alien life. Yet, despite decades of searching, we have found no definitive evidence of extraterrestrial civilizations. no radio signals, no evidence of spacefaring species, no proof that we are not alone. Several possible explanations for the Fermi paradox have been proposed, each suggesting different reasons why intelligent life may be rare, or why we have not yet made contact with it. One possibility is that intelligent civilizations are incredibly rare, that while microbial life might be common, the emergence of advanced, technologically capable species like ours is exceedingly unlikely. Perhaps civilizations, even if they do exist, rise and fall so quickly in cosmic terms that they don't overlap with one another long enough for communication or contact to occur. The timescales involved in the evolution of life and the development of technology are immense, and the window of opportunity for making contact may be fleeting. Another possibility is that intelligent civilizations are deliberately avoiding us. This idea, known as the zoo hypothesis, suggests that extraterrestrial civilizations are aware of humanity but are intentionally choosing not to communicate with us, perhaps out of concern for disrupting our natural development. It's also possible that advanced civilizations may operate under principles of non-interference, choosing not to make contact until we reach a certain level of technological or philosophical maturity. Alternatively, the answer could lie in the nature of the signals we are looking for. Our search for extraterrestrial intelligence, SETI, primarily focuses on detecting radio signals or other forms of electromagnetic communication, but it's possible that alien civilizations are using entirely different methods of communication, perhaps forms of quantum entanglement, or technology far beyond our current understanding. The signals we are searching for may simply not be detectable with our current instruments, leaving us unaware of their presence. Finally, there is the possibility that the universe is teeming with life, but we have not yet developed the technology or methodology to find it. As our own understanding of the cosmos grows, especially with new tools like the JWST, the search for alien life will continue to evolve. The telescope's ability to study the atmospheres of distant exoplanets could reveal biosignatures, signs of life, or other anomalies that could provide crucial answers. In this sense, the Fermi paradox may simply reflect the limitations of our current search. The Fermi paradox is a deeply thought-provoking challenge to our place in the universe. It raises essential questions not just about life elsewhere, but about the nature of existence itself. Are we truly alone, or are the answers just beyond our reach? With each new discovery, the mystery deepens, and the search for extraterrestrial life remains one of the most exciting and fundamental quests in science. As humanity pushes the boundaries of space exploration, the question of whether we are alone in the universe looms larger than ever. The discovery of thousands of exoplanets in the habitable zones of distant stars, combined with the vastness of the universe, suggests that life elsewhere might not just be possible but likely. However, this raises an unsettling question. If intelligent life is so probable, why haven't we found any sign of extraterrestrial civilizations? The answer may lie in a theory known as the Great Filter. This theory attempts to explain why, despite the vast number of potentially habitable planets, we seem to be utterly alone, or at least unable to detect any advanced civilizations. The Great Filter is a concept introduced to help explain the Fermi paradox, the puzzle of why the universe appears so empty despite the high probability of intelligent life. The filter is a bottleneck in the evolutionary process, a crucial step or series of steps that most civilizations fail to pass, preventing them from reaching an advanced, detectable stage. In other words, the filter represents a stage of development that is so difficult or unlikely that the majority of civilizations simply don't make it through. If this is the case, it would mean that advanced civilizations are either extremely rare or they self-destruct before they can spread across the galaxy. The Great Filter could be located at any point along the evolutionary timeline, from the emergence of life itself to the development of advanced technology capable of interstellar communication. One of the most chilling possibilities is that the filter lies behind us, meaning that the rare and improbable event of life's emergence on Earth might be one of the hardest hurdles in the entire cosmic timeline. If that's the case, it suggests that the rise of life on Earth is an extremely rare event, and that the conditions for life to form elsewhere may be far more specific and improbable than we realize. In this scenario, we could be the exception to the rule, a rare fluke of evolution in the cosmos, with no other examples of life existing elsewhere. Another possibility is that the Great Filter lies ahead of us, in our future. This would mean that while life may be common in the universe, the majority of civilizations never survive long enough to achieve interstellar travel or make contact with other civilizations. Perhaps the development of advanced technology inevitably leads to self-destruction, through warfare, environmental collapse, or some other catastrophic event. the history of human civilization with its potential for nuclear war and environmental degradation, could be an ominous warning that we too might be headed for our own filter. If this is the case, the challenge facing humanity is to identify and overcome the great filter before it's too late. Alternatively, the filter could be a series of smaller steps scattered throughout the evolutionary process. Perhaps intelligent life is common in the universe, but the path to developing technology that can communicate across vast interstellar distances is fraught with challenges. Civilizations may fail to make the technological leap necessary for interstellar communication or space exploration, or they might not last long enough to reach that stage. This scenario suggests that while life may be abundant, the number of civilizations capable of reaching the next stage of galactic presence, traveling beyond their home planet or contacting other civilizations, might be much smaller than we think. The implications of the Great Filter are profound. If the filter lies behind us, it would mean that life is extremely rare, and we are lucky to have emerged in the first place. If the filter lies ahead of us, it means that humanity faces an uncertain future, and our survival may depend on our ability to navigate existential threats. Either way, the concept of the Great Filter forces us to confront uncomfortable truths about our place in the universe. Are we a rare and fragile anomaly in the cosmos, or are we on the precipice of a future that could spell our extinction? The answer to the Great Filter question could shape the way we think about our future and the future of humanity's place in the vast, mysterious universe. The idea of communicating with extraterrestrial intelligence has captivated the human imagination for centuries. For millennia, we have gazed up at the stars, wondering if we are alone in the universe or if there are other civilizations out there, waiting to make contact. The search for extraterrestrial intelligence, SETI, is the scientific effort to detect signals from other civilizations in the cosmos. It is one of the most ambitious and profound endeavors in modern science, driven by the tantalizing possibility that, among the billions of stars in the universe, some might host intelligent beings capable of communication. Yet, despite decades of searching, SETI has yielded no definitive evidence of extraterrestrial life. The silence of the cosmos raises important questions. Are we truly alone, or are we simply looking in the wrong way? SETI's history dates back to the 1960s when astronomer Frank Drake conducted the first radio search for extraterrestrial signals. Drake's pioneering work involved scanning the star Tau Ceti for radio transmissions, marking the beginning of a scientific quest that would span decades. Since then, SETI has expanded to include searches for various forms of electromagnetic radiation, such as radio waves, laser pulses, and even optical signals. The premise is simple. If intelligent life exists elsewhere, it is likely that they would be transmitting signals, whether for communication, exploration, or perhaps just as a byproduct of their technological activities. One of the most well-known efforts in SETI has been the search for narrowband radio signals, a technique that looks for artificial signals that stand out from the natural radio noise in space. This search has focused on stars that are similar to the Sun, in the hope of finding planets that might harbor life. The use of large radio telescopes such as the Arecibo Observatory, until it was decommissioned in 2020, and the Green Bank Telescope has allowed scientists to scan vast regions of the sky, listening for signals that could indicate the presence of intelligent life. These efforts have led to some intriguing findings such as the famous WOW signal detected in 1977, a brief, unexplained burst of radio waves from the constellation Sagittarius. Despite extensive follow-up searches, the signal was never repeated, leaving it as one of the most enduring mysteries in SETI research. However, after decades of searching, SETI has not yet detected any confirmed signals from extraterrestrial civilizations. This lack of evidence has led to a variety of possible explanations, some hopeful and some sobering. One possibility is that intelligent civilizations are simply too far away for us to detect their signals. Given the vast distances between stars, even a signal traveling at the speed of light could take thousands or even millions of years to reach us. Another possibility is that alien civilizations are using communication methods far different from our own. Our search for radio waves may be missing the signals that extraterrestrials are using. Perhaps they are communicating with lasers, neutrinos, or other forms of energy that we are not yet capable of detecting. Another explanation for the silence of the cosmos is that advanced civilizations may be deliberately avoiding contact. The zoo hypothesis, as it is sometimes called, posits that extraterrestrial civilizations are aware of humanity but choose not to make contact, perhaps for ethical or scientific reasons. Just as we might avoid disturbing an isolated tribe in a remote part of the world, extraterrestrials might choose to observe us without interference until we are ready for contact. Alternatively, civilizations might operate under the principle of non-interference, opting to avoid revealing themselves until we reach a certain level of technological or philosophical maturity. Yet another possibility is that intelligent civilizations are rare, and we are one of the very few, if not the only species in the galaxy capable of interstellar communication. If this is the case, the lack of signals might simply reflect the inherent rarity of intelligent life. The vast majority of stars in the universe are not surrounded by habitable planets, and even if they are, the conditions for life, let alone intelligent life, may be much more specific than we can imagine. The Fermi paradox, which highlights the contradiction between the high probability of intelligent life and the lack of evidence for it, remains an unresolved mystery that continues to fuel SETI research. As we continue our search for extraterrestrial intelligence, new technologies and methods may improve our chances of success. The James Webb Space Telescope, JWST, for example, is capable of observing distant exoplanets in unprecedented detail, searching for chemical signatures that could indicate the presence of life. The study of exoplanet atmospheres may reveal biosignatures, indications of biological processes, that could serve as a stepping stone toward detecting extraterrestrial intelligence. Meanwhile, advances in artificial intelligence and machine learning could help scientists analyze the vast amounts of data collected from radio and optical searches, making it easier to detect patterns that might indicate the presence of alien signals. Despite the challenges and uncertainties that accompany SETI, the search for extraterrestrial intelligence remains one of the most profound and important endeavors in science. Whether we find evidence of alien civilizations or not, the very act of searching expands our understanding of the universe and our place within it. As we continue to push the boundaries of exploration, we may one day find the answer to one of humanity's oldest questions: are we alone in the cosmos? As humanity pushes the boundaries of space exploration, one of the most revolutionary tools in our arsenal is artificial intelligence, AI. From analyzing the vast amounts of data collected by telescopes to controlling autonomous spacecraft, AI has become indispensable in the quest to understand the universe. In many ways, AI is not just an assistive technology but is becoming a co-pilot in our exploration of space, helping scientists navigate the vast, unknown realms of the cosmos with unprecedented efficiency and precision. One of the most significant ways in which AI is aiding space exploration is through the analysis of data. Space missions generate enormous amounts of data, from images and spectrographs to sensor readings and telemetry. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope, JWST, are capturing billions of bytes of data every day as they scan distant galaxies, exoplanets, and cosmic phenomena. Analyzing this data is a monumental task, one that would be impossible for human scientists to perform manually. AI algorithms, however, are capable of processing this data quickly and efficiently, identifying patterns and anomalies that might otherwise go unnoticed. Machine learning, a subset of AI, is particularly powerful in this regard. By training on vast datasets, machine learning algorithms can learn to recognize features in astronomical data, whether it's the spectral signature of an exoplanet's atmosphere or the faint glimmer of a distant star. These algorithms can also improve over time, becoming more accurate and efficient as they process more data. For example, AI has already been used to identify new exoplanets by analyzing light curves from distant stars. These light curves show how a star's brightness changes as a planet passes in front of it. While this data can be noisy and difficult to interpret, machine learning algorithms can sift through it and pinpoint patterns that suggest the presence of a planet. AI is also transforming the way we explore and navigate space itself. Autonomous spacecraft, powered by AI, are becoming an essential part of space exploration. Space agencies like NASA and ESA, European Space Agency, are developing spacecraft that can make decisions on their own, without waiting for instructions from Earth. This is crucial because of the vast distances involved in space travel. A signal from Earth can take hours or even days to reach distant spacecraft, making real-time control impossible. AI-enabled spacecraft can autonomously adjust their trajectory, avoid obstacles, and even perform scientific experiments, all without human intervention. One of the most notable examples of this is NASA's Perseverance rover on Mars, which uses AI to navigate the Martian surface and choose the best paths to travel, maximizing the rover's ability to conduct science while minimizing the risks associated with driving on a foreign planet. Another exciting development in AI's role in space exploration is its potential for simulating and modeling complex cosmic phenomena. From simulating the formation of stars and galaxies to predicting the behavior of black holes, AI can help us test hypotheses and create detailed models of the universe. These simulations are crucial for understanding the underlying processes that govern the cosmos, but they require immense computational power. AI algorithms, particularly deep learning networks, can accelerate these simulations by identifying the most relevant variables, optimizing calculations, and running multiple scenarios simultaneously. AI is also playing a significant role in the search for extraterrestrial life. The vast amount of data collected from the search for extraterrestrial intelligence (SETI) is often overwhelming, and AI is being used to analyze radio signals, optical signals, and other potential signs of alien civilizations. AI's ability to sift through large datasets, recognize patterns, and make predictions could help detect faint signals that might otherwise be missed. In a way, AI is becoming a digital detective, looking for the subtle clues that might point to extraterrestrial intelligence. Despite all the advancements AI has brought to space exploration, it also raises important questions about the future of human involvement in space. As AI takes on more tasks, from data analysis to autonomous navigation, will humans become sidelined in the exploration of the cosmos? Some worry that relying too heavily on AI could lead to a disconnect between humans and the very discoveries we make. However, others argue that AI will augment human capabilities, allowing us to explore and understand the universe in ways that would have been impossible on our own. By using AI as a tool to enhance our scientific capabilities, we may be able to answer questions that have puzzled humanity for centuries, such as the nature of dark matter, the origins of life, and the potential for life beyond Earth. In the coming decades, AI will undoubtedly continue to play a pivotal role in space exploration. As our missions become more ambitious, from sending humans to Mars to studying the outer reaches of our solar system, AI will help us navigate the complexities of space. In many ways, AI is already shaping the future of how we explore the stars, offering us new ways to understand the universe and our place within it. The cosmos is vast and mysterious, but with AI as our ally, the possibilities for discovery seem endless. The future of space exploration is one of boundless possibilities, driven by both our innate curiosity and our desire to ensure humanity's long-term survival. As we look ahead to the next few decades, space exploration is poised to take a monumental leap forward. Human missions to Mars, the potential colonization of the Moon, and the development of space tourism are just the beginning. At the heart of this transformation lies a combination of cutting-edge technology, including AI, robotics, and sustainable energy solutions, along with an enduring human spirit of exploration and adventure. Perhaps one of the most significant goals for humanity in the coming decades is the colonization of other planets. Mars has long been the focus of these efforts, with multiple space agencies including NASA and private companies like SpaceX, working on the technological and logistical challenges of sending humans to the Red Planet. Mars, with its relatively Earth-like day-night cycle and evidence of ancient water flows, presents the most plausible candidate for colonization. However, the challenges are immense. We must figure out how to protect astronauts from deadly radiation, establish a sustainable food and water supply, and build habitats capable of withstanding the harsh Martian environment. The dream of creating a permanent human settlement on Mars is not just about survival. It is about extending humanity's reach into the cosmos, ensuring that we are not bound to a single planet, and safeguarding our species from potential extinction events on Earth. The Moon, too, plays a crucial role in humanity's future in space. NASA's Artemis program aims to return humans to the Moon by the mid-2020s, this time with the goal of establishing a sustainable presence there. The Moon could serve as a stepping stone for future missions to Mars, providing a base for launching deeper space missions and a site for mining resources, such as water ice, which could be used for fuel. Establishing a permanent lunar base could also offer scientists a unique vantage point for studying the cosmos, allowing us to conduct experiments in a low-gravity environment and observe the universe without the interference of Earth's atmosphere. Artificial intelligence and robotics will be crucial in making space exploration a reality. Autonomous robots and AI systems will help us overcome the vast distances and harsh environments of space. These technologies will assist in everything from building habitats on Mars to scouting potential landing sites and analyzing samples. In the coming years, AI will likely play an even larger role, helping to coordinate space missions, manage resources, and ensure the safety of astronauts by monitoring their health and well-being. As we venture farther from Earth, we will need intelligent systems capable of operating autonomously, making real-time decisions without relying on communication from Earth. But beyond technology, the human spirit remains the driving force behind space exploration. The pursuit of knowledge, the desire to push the boundaries of what is possible, and the fundamental urge to explore the unknown have always been intrinsic to humanity's progress. As we embark on this new era of space exploration, it is this spirit that will sustain us through the challenges and uncertainties that lie ahead. Whether it's the first human footprints on Mars, the discovery of alien life, or the creation of a self-sustaining colony on another world, the future of space exploration promises to be as much about the human experience as it is about technological innovation. Ultimately, the future of space exploration is not just about reaching new worlds, but about ensuring the survival and advancement of humanity itself. As we look to the stars, we must ask ourselves not just how we can explore the cosmos, but how we can become a part of it, how we can evolve into a multiplanetary species capable of thriving in the vastness of space. The journey ahead will require collaboration, innovation, and resilience, but the rewards are boundless. The idea that our universe is just one of many is a concept that has captivated the imagination of scientists, philosophers, and science fiction writers alike. This idea, known as the multiverse theory, suggests that the cosmos we see around us may be only a small part of a much larger, more complex reality. According to the multiverse hypothesis, there could be multiple universes, each with its own set of physical laws, constants, and even versions of reality. These universes may coexist, separate from one another, forming an enormous multiverse that stretches beyond our understanding. But could the multiverse theory hold any scientific validity, or is it simply a speculative idea? The multiverse theory has its roots in several areas of modern physics, particularly in quantum mechanics and cosmology. One of the most popular forms of the theory arises from the concept of cosmic inflation, a period of extremely rapid expansion that occurred in the first moments after the Big Bang. According to this theory, inflation caused different regions of space to expand at different rates, leading to the creation of separate bubble universes within the larger multiverse. Each bubble could have its own distinct properties with different physical constants, laws of physics, and even dimensions. These bubble universes could be completely disconnected from each other, existing in parallel and unaffected by one another. Another aspect of the multiverse theory comes from the many worlds interpretation of quantum mechanics. In quantum mechanics, particles don't exist in a single state but rather exist in a range of probabilities until they are measured. The many worlds interpretation posits that when a quantum event occurs, such as a particle being measured, all possible outcomes actually happen, each in a separate, parallel universe. This suggests that for every decision or event in the universe, an infinite number of alternate realities may be created, each corresponding to a different possible outcome. If true, this would mean that there are countless versions of ourselves, living in parallel worlds where different choices and events unfolded. The concept of the multiverse also has implications for the fine-tuning problem, which is the observation that the conditions of our universe appear to be perfectly suited for the existence of life. The laws of physics and constants, such as the strength of gravity and the charge of the electron, are finely tuned in a way that allows stars, planets, and life to exist. Some proponents of the multiverse theory suggest that this fine-tuning may not be as remarkable as it seems. If there are countless universes, each with different physical laws and constants, then the existence of a universe like ours, one that supports life, may simply be a result of chance. In this view, we are not uniquely special. We are simply one of many universes where conditions happen to be just right for life to emerge. Despite its intriguing possibilities, the multiverse theory remains highly speculative, and there is currently no experimental or observational evidence to support it. The idea challenges the very nature of science, as it posits the existence of universes that are fundamentally unobservable and beyond the reach of any technology or measurement we could ever conceive. Some critics argue that the multiverse theory is not testable or falsifiable and therefore cannot be considered scientific in the traditional sense. Others, however, contend that while we may not be able to observe other universes directly, the multiverse hypothesis could still be an essential part of a larger theory of everything, helping to explain the underlying structure of reality itself. The multiverse theory raises profound questions about the nature of existence and our place in the cosmos. Are we truly alone in our universe, or could there be other versions of reality, with other forms of life, other versions of ourselves? As we continue to push the boundaries of science and explore the mysteries of the universe, the multiverse theory remains one of the most tantalizing and perplexing ideas, suggesting that the universe we see around us might only be a small piece of a far more expansive, complex, and mysterious reality.